This media was gratuitously produced by Clear Contributions Audio and Video. The intellectual property contained within belongs to Dr. Barbara Van Kyken. Clear Contributions. Let's have clarity.
All right, let's see. A is here. Yep. All right, any issues with anything about the name or anything where you're not really sure how that worked out that way?
Yeah, how do we put the numbers up there?
Okay, so you don't have a functional group, so you gotta give the lowest number possible to a substituent. So anywhere you start numbering is number 1, so that's kind of, that doesn't really help you out. But because you have two things right next to each other, that means that's got to be your 1 and 2. So that's where you start numbering. So you go 1, 2, 3, 4, and then you go the other way, 1, 2, 3, 4, and see if there's one that's better than another for the chlorine.
Right.
Since that's the same, everything's a tie. You have 1, 2, and 4, either way that you go, but different substituents. So that means you're at the last tiebreaker rule because everything is tied. So you put the lowest number to the one that's first alphabetically of these two choices here. B is here. It's a little hard to see maybe, but the big trick there is make sure that you turn the corner so you get the longest continuous carbon chain. So that is a heptane, and then you have methyl groups on carbons 2 and 5. If you number the opposite direction, they would be on 3 and 6. So that's why you're numbering this way. 2,5-dimethyl heptane. Fine. Any questions or problems with that? It looked like C was a little bit of a problem for a lot of you. Let's dissect it out. So, it looks like I think you're probably all okay with how to find the functional group and parent hydrocarbon substituent for this. The numbering is chosen based not on the functional groups this time because you're a tie. It would be 1, 3 this way and 1, 3 this way. So because it's an exact tie for the functional groups, now you have to look at the substituent, and that's why you end up with this numbering system here. That's fine with the methyl group. So you have the methyl, and then the bute and the ene. That part's fine. It's just where the numbers are placed, and the prefix here is a little bit of an issue. So, if you're writing it out, normally you would have methyl, butane, and you cross it off, and you have the ene ending. It's the ene that there's 2 of. There's 2 double bonds, not 2 butane parent hydrocarbons. So the di goes here. Okay, and then the numbers, it's true that you can put numbers out in front of the parent hydrocarbon, and that's perfectly acceptable. The newer way to do it is to put the numbers by the functional group or the substituent. And so through the book, I'm just going to do that just so it's consistent. But I wouldn't mark it wrong for having the 1 and 3 out in front here. It's just that the die has to go with it. But just to keep it consistent, I'll put the numbers here. Yeah, like that. Okay, so the di or tri goes with the functional group or substituent specifically. Any other questions about that one? Here. Okay, that's fine with how it's diagrammed out and how everything's put in place here. And then this has to be the number 1 because you're giving the lowest number possible the carbon directly attached to the functional group as opposed to the substituent. So that's what I'm testing for on this particular question. So this is carbon 4. If you put a 1 here by the all, I won't mark it wrong. Technically, you don't have to have it because if it's a cyclic compound and you have a functional group, by definition, that has to be in position 1 because you're giving it the lowest number. So either way. Any questions about D?
Shouldn't there be cyclone?
Yeah, we're recycling as well.
Thank you. Very good. I did miss that part.
No worries.
Good. All right. It's here. Okay. Any issues that you have with that? There's a real minor one. It's not a huge issue. All you're dropping is the E here because it's still a pentane. But that's very minor. You only drop the entire ane ending if you're replacing it with ene or ein.
Why do you duplicate the N? I always put one N.
Yeah, so everything gets a location number, even if it's the same location. Just for clarity. Yeah. So if you had a trimethyl, then you need 3 numbers or 3 N's or whatever.
So for alcohol, they just drop the E.
That's true.
Oh.
Any other questions about E? F, over here. Okay, this one you get the same numbering for either direction for the functional group, and so you have to look at the locations for the substituents to decide the numbering. This one actually go this direction because then you can get the number 2 substituent.
So when putting it down, would you go alphabetically or a small number in the front?
Alphabetically. So that's kind of why I'm having you do it in the steps that I have also. That's step 2 is write these in alphabetical order, and that's so that you're not thinking in terms of numbers. You don't put the numbers in until step 4, and they just go where they go. Okay, it looks like G is an issue, and I've heard some of you say the same thing, that you're not sure what to do with this. Remember, when you have the parentheses, right, it means that that group is attached to the carbon that's just to the left of it, but it's not part of the chain. So another way that you could write this would be, here's the carbon here, and it has 2 ethyl groups attached to it, like that. And then think about it here.
Oh, so that's not
There's a parent hydrocarbon, we have a hexane, and we have ethyl substituents. 3 is a diethyl. Step 4, assign numbers. You can get lower numbers going left to right. So it's 3,2-diethyl hexane. If it's hard for you to read, this is 3-ethyl-4-methylhexane 1-all. And that's correct. So the number 1, almost.
Wait, is there an ethyl group attached?
Did you the ethyl because of the zigzag corner?
This is an ethyl group right here.
Oh, there's not another C in the corner, so they just thought it was an ethyl. Come on.
Oh, I see.
There's an ethyl.
So there's no methyl.
So my computer does a little bit of an odd thing where it normally it would just look like that, right? My computer puts a carbon on the end, even though it could be drawn like that where it's implied. But that's an ethyl group.
Shouldn't it be ethyl for fluoro?
I see.
Cyclohexane?
I see. Now I got rid of the cyclohexane. And the one isn't needed for the all, but if you put it in this. Anything else you want to comment on that? Okay, I has it's fine. Almost. So the parent hydrocarbon has to include the functional group. That's why it's on this side of the ether instead of the other side, because we have the functional group double bond here. That's a butoxy group. That's fine. It's attached to carbon number 1 of the parent hydrocarbon. The parent hydrocarbon is numbered this way so that you're giving the lowest number possible to functional group carbon. And then if you put a 1 here for the ene, that's fine. Technically, you don't have to have it for a protein, just because either place that you put it has to by default be carbons number 1 and 2, because you're giving the function the lowest possible number. But again, that's one of those random exceptions. So 1 butoxypropene, or I will accept 1 butoxyprop 1 ene. Don't get heartburn if you're having a hard time with the exceptions for numbering. Okay. J.
Right there, right in front of you.
I see one thing to correct. It's a propyl because it's a substituent. So the substituents have YL endings.
And then
Butan. All right, and the last one, K. Anything? No, that's fine too. I think that you mostly have it, but I'm seeing some boo-boos. So, how about if part of your homework you do 40 and 41 tonight?
sorry, 40 and 41.
40, 40, 41, 42, I think.
No, 40, 41.
40, 41, okay. Okay, so chapter 2 is going to add on to this. On your bookmark, you have the 5 steps for naming a compound using IUPAC. We've went through the first 4 for the chapter 1. Step 5 is chapter 2. That's just going to complete the sequence for you, but it's going to take a fair amount of work to help you see how to name the stereochemistry. Hopefully you got chapter 2 PDFs last night. Okay, and I'm already applying my own corrections to things. The stereochemistry is how everything projects in space. It's very important because, among other things, it can affect how it interacts with biological molecules like enzymes. It also could affect some of its physical properties, such as boiling point temperatures or melting point temperatures in some cases. So you need to describe how it projects in space. For example, these 2 molecules would have the same base name because they have the same groups attached and the same number of carbons and, attached to the same thing, but they don't match up in terms of how they line up in space. So if you had an enzyme that had a binding pocket for the green over here, and you had a binding pocket for the orange here and black here, it's not going to work to try and bind this to that same enzyme. It's not going to line up correctly. And even if you can get 2 of the things to line up, a third doesn't. And one really common example for a situation where a drug had 2 different kinds of stereochemistries is thalidomide. Thalidomide was prescribed for expectant mothers in the 50s, and it helped with morning sickness. And the one form bound to the enzyme that, a target enzyme, and it did the job. It helped prevent morning sickness. The other one, though, bound to something in the fetus, in the enzymes in the fetus, and it caused severe birth defects where the children were born without arms and legs and everything. Known as thalidomide babies. And unfortunately, the drug interchanges in the body, and so even if they tried to give the woman the one that was effective for the birth or for the morning sickness, it still caused the birth defects because it would change into the other one. But medications, quite often, it has to be a specific stereochemistry, or it either won't be effective or it's going to cause harmful side effects by binding to a different target. So you need to describe in the name of the molecule whether you're talking about the way this projects into space or the way this one projects into space. So this whole chapter is just to help you see how to assign a label to different types of stereochemistries. Okay? We're only going to get through probably point 1 today, how to define and recognize chirality centers. And if you're not sure where I am right now, I'm on the textbook just because I wanted you to build some models, and I have the graphics for those models in the textbook chapters. All we're going to do today is mostly work with a molecular model kit rather than your lecture outline. And I'm just going to help you try to visualize some different concepts. So, there's an example of 2 molecules that you can build. And one thing that I want to teach you is how to interpret this kind of representation. So if you have a hatched line like this, just like if something's far away from you, it's getting harder to see, it's getting kind of fuzzier or something less clear, that hatched line kind of represents it's getting a little bit more difficult to figure it out. So this means that it's going away from you. The solid wedge is coming towards you, and any regular lines are in a plane. So it looks like, I don't have the right colors here, but it looks something like this. So you're lining things up in a plane, and then you have something coming towards you and going away from you.
take this one, the long one, and the other one?
You can use either one that you want. The long bonds are usually if you're going to make double bonds and you need something flexible so it can curve around, but you can use whatever you want to. You can use white instead of yellow.
I thought we used orange. Doesn't white mean hydrogen?
Yeah. Either one. Whatever you like.
You want us to put hydrogen for green one?
It doesn't matter. I just want you to have a carbon with 4 different colors attached and then make the mirror image for that. Right now. Here. Yeah, when they're new, they're going to wreck your thumbs. I know. I got some kits for biochemistry that were big molecules, and I sat one day and put all the kits together, and by the time I went home, I was going,
My old biology class, so we just make this, the fatty acid chain.
Uh-huh.
So it's like, I don't know, really like 15 carbon.
Probably at least, yeah.
Yeah, and it was like just super long. It took like all the last year to make it.
Uh-huh.
And she was super particular about it also.
Oh,
I should know that right now. That's why I remember with these things.
maybe that's why she did it, so you'd have that bitter memory that would stick with you.
Seriously.
Stronger hands.
I don't think I need to do this.
Why do you do?
Okay, you're making a pair. One thing that I want you to do is convince yourself you can't match them up. Any way you twist it. Yeah. Build these two.
Oh.
Yes.
Still got it.
You could have got one of those that
And if you don't have a molecular model kit, it's going to be real critical for this chapter specifically, and it will also be helpful for some of the other stuff that we have coming up with reactions. And it's already been billed with your tuition, so just go to the bookstore and ask for it, and they'll hand it to you. You got it?
yeah.
Looks like most of you are there. What I want you to notice is it doesn't matter how you try and match all 4 atoms up, you'll always have 2 that match and 2 that don't. You can't get them to be the same. Because you can always get two to match and two that don't match, what it means is if you swap any two atoms, pick any two and swap them, now you'll have something that lines up. So that'll be helpful for later. You switch any two, you got the same molecule, switch them back, you got opposite molecules or mirror images. Are you kind of okay with that concept? Try to line them up, you can only get two. Can't get the other two. No matter what the colors you try to line up. Got those two, but not those two. Okay. Replace replace the green one with the white or whatever you used for yellow. On each one of them. Replace the green one with white or yellow so that you have two of the same color. What do you notice if you replaced it?
I'm confused.
You notice you're confused? Okay.
All of ours match, mine match up.
Okay, they match up. That's fine. That's what I wanted you to notice. You notice if you have two of the same, even though it looks like a mirror image, you can set them next to each other so it looks like it's a mirror in between them, but they're really the same molecule. Right? So the only way that you have two different possibilities is if you have four different colors on there. That's what I need you to recognize.
Oh, if you have three,
If you have three different
it's
colors,
gonna be.
then it's all the same. So you wouldn't have to tell somebody that has a specific stereochemistry because there isn't an option for two different possibilities. Okay? If you have four different atoms or groups attached to a carbon, that's called a chirality center. And that's when you have to describe what the stereochemistry looks like. All right, so if you notice, and you have this in your workbook on, also if you have your workbook open, or you can have the textbook for right now. There's a skills check that I wanted to go through and make sure that as a first step, you can recognize that a carbon has four different atoms or groups attached to it, and so therefore you could identify that there is a chirality center there that you're going to have to do something about stating what the stereochemistry is. Okay? And first, I want to say one additional thing. Right now, you're just working with simple colors, but it could be an entire group that's different. So let's say you have a methyl group attached to a carbon and an ethyl group. Those two project into space very differently. A methyl group is a different shape than an ethyl group. So if you were going to bind it into an enzyme binding pocket, they would fit differently. And so it isn't just if you have different colors or different atoms, it's also if you have different groups. So for A here, do you notice if there is a chirality center, and if so, where is it? In the molecule. You have to have four different atoms or groups attached to the carbon. What's something that you can rule out right away?
Double bond?
The double bond, because these carbons, since they have the double bond here, can only have two additional things attached to them, and so they can't have four things attached. So don't look at anything where you got a double bond or a triple bond. You're focusing on carbons that have only single bonds to them, so you can have the option for four things attached to them. What's another thing that you notice that you can rule out right away? Good. If a carbon's bonded to more than one hydrogen, think about hydrogens as being like your white little spheres. That's like having 2 or 3 of the same exact color attached. That can't be a chirality center, so don't bother with those. Also, you're only looking at carbons generally, because generally that's the only thing that's going to have 4 things attached. Okay, so that focuses you down on where's the chirality center here.
Let's see.
They wouldn't have one, right? Because there's just atoms attached to it.
Actually, it's this one because this has a different shape than this does. So you're not looking just at the atoms that are attached. You're looking at the whole group to see, because this will project differently in space than this one will. Okay, so this is a chirality center because you have a hydrogen, an NH2, a methyl group here, and then this vinyl group.
What would you call that group?
A vinyl group.
Vinyl?
Vinyl. Yeah, those are vinyl carbons, kind of going back to that pre-class check that we did at the very beginning of the semester, but we're going to hit that again in chapter 3, so don't worry about it. We'll come to it again.
Even though it's hooked onto 2 different carbons, they don't count as the same thing because the one has like a different shape than the other.
Right. Because you're trying to say, like, for instance, if it was attached to an enzyme, those would be different. So here, let me build something similar to that. Let's say that this is a methyl group and an ethyl group here. Those project into space very differently. And so it matters whether it's here in the enzyme binding pocket or over here.
Okay.
Look at groups, not atoms. When you find a chirality center, you put a little star usually on it, or asterisk, like that. Okay, so that's a chirality center there. All right, we only have a couple more minutes. I just want to work through B, and then I'll show you how to do C, and you can do the rest of them for your homework. Do you see any chirality centers in B?
Yes.
Just the 2 carbons?
These 2 carbons right here, yep, are both chirality centers, so you put an asterisk by both of them. I'll talk you through it. You can eliminate any carbons that have multiple hydrogens. Those can't be chirality centers, and so just focus on these 2. This carbon has a bromine, a methyl, an ethyl, and all of this. That's 4 different kinds of groups or atoms attached to it. It's the same thing over here. This carbon has a bromine, a methyl, an ethyl, and all of that. 4 different things attached to it. Okay? Now I will show you a cyclic compound and how you decide with that one. Since the carbons in the ring that don't have anything attached to them have only 2 bonds, and so therefore that must be 2 hydrogens attached to it, we're not going to look at those as possibilities. We're only going to focus on whether, is this a chirality center and is this a chirality center? It might help you if you fill in the missing or implied hydrogens to see everything. Since that had 1, 2, 3 bonds, that means there's a 4th here that's a hydrogen. And the same thing here. Okay, now it's trickier here because it's hard to see what your 2 other groups are. You see you got a hydrogen and a chlorine. What are these groups here? You know, it's like it's a ring. How do you do that? So what you do is you mentally detach it here and think about what this group looks like. So if you're going this way, you have a CH2 and you have a carbon with a CH3 on it, and you have a CH2, CH2, CH2. Okay, so that's going this way around the ring. Okay, now you mentally detach this side and you go this way around the ring and write what that is. So you've got a CH2, 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 carbon with a methyl group, and a CH2. See how that's different when you're going this way versus this way? So you can mentally sometimes just, go, is this different than if I go this way instead of writing it all out? But because you have 4 different groups attached there, that's a chirality center. And you do the same thing up here. You got a hydrogen and a methyl group. Those are different. So now if you're going this way, it's CH2, CH2, CH2 carbon with a chlorine. Those are different. There's a chirality center. Okay, you can finish those. Like I said, this is just to help you see. Do I have to put something special in the name for this just because I do have a possibility for different kinds of stereochemistry there?
Where are these?
Where are they in your workbook chapter since I was working on the textbook? Page 3? Okay. Of your chapter 2.
Is it an email you sent us?
Yeah.
Yes, it's in the email, and I said I was going to get the hard copies, and I totally slipped my mind. I'll get you some hard copies for Monday.
So it's actually in the Word document, page 54 at the bottom.
Yep.
Page 54. Okay.
And so we finish the rest of the page.
Yeah.
I like this.
All right. Have a great weekend.